In the last podcast we have seen a bit of theory and introduction to the analysis of variance ANOVA method. Now we will show how to apply this method or alternatives with R. First we will see how we do an ANOVA by hand in R. Then we will see how we check the normality assumptions that are necessary, and we will see alternatives of this ANOVA. We will also use a tool that was developed at EIS to visualize ANOVA and related methods. After that we will do the post hoc testing, so we will do this error inflation corrected T testing or Wilcoxon testing depending on the properties of the data. We will with that really detect differences, and we will do that directly with a tool developed by EIS that gives you really nice information about your data. We will see what we do if the assumptions for an ANOVA are not met. So if we have a non-normality of the residuals, as explained in the last podcast, then we do the Kruskal test or Kruskal-Wallis method. If we have normality but the variances do not seem equal, we do the so-called one-way test that you also find in the script by Sabine. And if normality is there and the variances look equal, then we really do the ANOVA. To test this normality assumption, we will use the ANOVA command in the case of one-way test and regular ANOVA. We will just see that in R now. So let's go into R. I have already prepared some files there. So let us first put the script size a bit larger. So I do change directory. I have it stored in a little bit complicated structure. I call this R tools, and I have a version here. And here I can open the script, it's called example. So let us first see what we need. So if you want to run the tool that will be presented later on, you need the package called multcompview. And if you do not have this package, and I assume you do not, then if you run this script the first time, you have to say install.packages and multcompview. And then you have to choose Switzerland as your mirror. So this is what you should do right now before you continue with the podcast. Now that you have done this, we have to read in our data. And let's have first a look at the data file itself. It's called example data. It's a CSV format. Of course, you can prepare that in Excel. And what we see in this file, if it will open, is that we have here a value called Gewicht or weight, and we have a variable called art or species. So we have different species here in the right column, and we have weights of them in the left column. So we see we have 4 different species, so this is a typical case for an ANOVA. So let's close this here and import it into R. So that's the first line here, Control R. And then you can look at the data, whether it was correctly imported. This looks all fine. So now we can do an ANOVA by hand. We just do that first. So this is the command AOV, data weight and data art. We save this object into the variable AN. We can display AN here. And what we see is we get some statistical values, but we do not get the p-value yet. The p-value you only get if you type summary of ANOVA here, Control R. And now you're in the nice case, you have a p-value, so you know that there are significant differences between these 4 different types of animals or plants it actually is. And now you know there is difference, but you don't know where, so you have to do a post hoc testing. But before we come to the post hoc testing, we will see how we test for the normality assumption. There are various ways. You have seen the QQ norm. And now the idea is that you say $AN$ to access the residuals. And then you see they lie more or less on a line. There are of course tests. We have seen that last time. Shapiro.test of $AN$resid. You can also do that and we get a p-value of 87%. This looks fairly normal. And we can also do a Kolmogorov-Smirnov test, but let's not do that. We have seen that in the lecture already. I have a tool developed at EIS that does this basically by automatism. So we can just load this file. It's called tests and visuals. If we open it, it looks like this. So there is quite some code inside, right? You do not necessarily have to go through all that, but you should understand the results that it produces. So I load this by saying source, press Ctrl R, and now I can actually apply this thing here. It's called test norm with. This is one function in this package. Press Ctrl R, and what I see is the picture on the right. So I see a QQ plot on the very right. I see in the title the values, the p-values of Shapiro-Wilk and Kolmogorov-Smirnov, and on the left I even see a histogram of the data with the kernel fitted density in blue and the normal density, so meaning a density, a normal distribution with the same mean and variance as the data, and we see how that overlaps. So in this case the two tests tell us that we have normal distribution. We have, I think, approximately 20 to 25 samples, but the QQ plot is a little bit, let's say, yeah, it's really difficult to just assess normality from the QQ plot if it looks like this. It's difficult to tell. So let's say we cannot really reject the null assumption, the null hypothesis of normal distribution, but for sure, I mean, like always, we cannot really prove it. Anyway, what we do first is an ANOVA, and this can be done either by hand as we have done just before, or you use this package with the function with ANOVA clusters. You press Ctrl R. Now the graphic window is not really what I want it to be, so close it and do it again. Now you see in the title the p-value of the ANOVA. What you see in the graphics is the different groups, so we named them D2, M4, Q3 and Z1. That's the levels of the factors. And you see the data, that is the rectangles you see in behind. So that's all the data points. Now you see a red interval. In between that interval you have the mean value, and the interval itself is a 95% confidence interval for that very mean. So it means that in the true population, if you would measure all possible plants with these 4 fertilizers, the chance of finding the real mean value of the population inside that red interval is 95%. Then blue, you see the standard deviations. We could also plot the variances there in order to give an optical idea whether these things are equal or not. There is also tests that test for equal variances. It's called f-test. Or var.test in R, but we don't go into details there. So that's the graphics, and now what's very important is the post hoc testing. The post hoc testing shows you with green letters to what clusters these groups belong. So the D2 belongs to a cluster A. Now if we compare D2 to M4, we do not detect any significant differences. That's why it has a letter A as well. If we compare that to Q3, A to Q3 or M4 to Q3, we do not see any significant differences neither. So the first 3 fertilizers, they do not show anything. in terms of differences. Now the fertilizer Z1 has a B, so there is a significant difference between Q3 and Z1. There is a significant difference between Z1 and D2, but there is no significant difference between M4 and Z1 because they both contain a B. Right? So with that, this is done by a post hoc t-test or Welch test with this alpha inflation correction. So we really can trust that together with the value of the ANOVA up here, there are significant differences and they are such as explained by the letters down here. Such letters you will find in lots of publications. Now, this was the ANOVA. We have tested the assumptions of the ANOVA with the normality test. We have seen that just before. So we need to do that separately, right? So we always need to say here ANOVA and then we test the residuals for normality. Now let's assume that we do not really have equal variances, right? If you look at the graphics, the variances optically do not seem equal. So we do a one-way test which works for unequal variances. It's here instead of ANOVA one way, and I just press Ctrl R. I see in the background the p-value changed, but the letters of course did not, because the RT test is automatically changing to a Welch test if the variances in the samples are not equal, so that is no difference there. Still, for the one-way test I need to check the assumption of normality, and I do that with the regular ANOVA. So I just do again this ANOVA, because the normality assumption of the residuals just depends on the group means, and the group means are the same in the one-way test as well as in the ANOVA. So I can do the same here with the same test here, and since we have already done that, we do not need to do that for the one-way test separately. Now if we assume that the normality assumption is not met, and we have seen that maybe this is, in this case I would say we can assume the data are more or less normally distributed, but let's just test what happens if we do not take the normality assumptions. And the method that you need to use there is called Kruskal-Wallis method. You can apply this with Kruskal.test of data $Gewicht tilde data $art, and you press Ctrl R, and then you see the p-value of the Kruskal-Wallis test. Again, the same problem as with the ANOVA. You have a p-value, so you know there are differences, but you do not know where they are located. And that's why we have, again, a tool from EIS, which is, again, in this tests and visuals package. You press here, instead of ANOVA, you have Kruskal-Wallis. So you go here, press Ctrl R, and what you see is on the title the p-value of the Kruskal-Wallis method. And then instead of confidence intervals you see box plots. This has something to do that in non-parametric tests you would have to use statistically data-intensive methods to infer some confidence intervals, which we do not do here. We just show box plots of the data and the data in rectangles behind. Again, we see groups, but now observe that the groups are slightly different. That is now very much due to the different kind of test that the Kruskal-Wallis is applying, and the pairwise test of course cannot be a t-test because we do not have normality, so it's a Wilcoxon or U-test. So what you see here is now you have cluster AB for the D2, and there are no significant differences between the first three. That's the same like before. But now the significant difference here of the last one is only with respect to Q3 and also with respect to M4. So I think M4 was not different to Z1 in the first version. And you do not have a difference between Z1 and D2. So it can be that indeed the Kruskal-Wallis test with its post hoc testing yields a different result than the ANOVA. This is due to the fact that we have different test assumptions. Shortly summarizing, we can say the following. First step is always the same. You need to import your data and check whether it was done correctly. Then I suggest that you try to do an ANOVA first by hand and check about the normality assumptions. If you have done that, then you can decide. I would always do first an ANOVA generally, just to see what happens. If you see here in the visualization that the variances are not equal, you can do a one-way analysis. And if you've done a one-way analysis and an ANOVA, and you have seen before that the data are not normally distributed, you can also check for the Kruskal-Wallis, or you can do that anyway to just see whether everything is consistent. If there are inconsistencies, and in most cases there are inconsistencies, it's important to name them transparently, to name different test results, and to give the reader of your paper or of your publication a good and transparent overview of the methods you have been using and of the results that you have obtained with them.